Hello, 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 hello. All right, so hello and welcome. Got another problem here we're going to work on, wildcard matching. So this is interesting. We just solved a problem very similar to this not too long ago. This is going to be in reference to glob patterns. I actually have read this already, so hopefully it's a little bit faster today. We'll see. I don't know. I guess I want to try to solve two hard problems back to back and then take a break. Let's see if we can do it. So wildcard. Actually, there'll be. Oh yeah, actually these we should be able to do all of these pretty quickly. The end queens as well as the wildcard matching. I have an idea for how to do these. All right, so we'll give us a +2. This is interesting. So we're gonna use a state machine for this, very similar to what we used last time. This is actually probably not too difficult of a problem. We might not. This might not be. Excuse me. This might not be as easy as I thought, in the sense that if we have 2000 and 2000, this might be, I don't know how efficient this is going to be. That's what I'm trying to say. But we're definitely going to use a state machine again. We can use a vector also instead of an array. Well, unordered map maybe. I'll come back to that in a moment. But yeah, so this is interesting. This is an interesting question. So yeah, we'll build a state machine, and then we'll memoize. And I guess we could use an unordered map for the memoization. That's fine. What do I want to do? Yeah, okay, all right, that's fine. So the state machine is going to be something like the following. So it's going to work like this. Given input string S and a pattern P, implement wildcard pattern matching with support for a question mark and an asterisk symbol, where question mark matches any single character, asterisk matches any sequence of characters, including the empty sequence. So we're going to have an epsilon jump for the asterisk. The matching should cover the entire input string, not partial. All right. The way this is going to work is we're going to use a state machine, and we're going to say if we reach, so we're going to loop over the characters in the string S. Is S the pattern? No, P is the pattern, excuse me. Loop over the characters in P, and if this character is it could be two special characters. We're going to do different things depending on what the characters are. Under normal conditions, we would say we're going to create a new state. So we have vector of states, and each of these states, they're really just going to be unordered maps, unordered maps of characters to other states, which would be, these states will be represented by integers. An initial state will be spell, be good. Okay, so create an initial map, and that's the first state. So we're going to create a new state, unordered map. We could just say state. The vector of states, and push back a new state. Hopefully I could do that. We're going to say state, new state, and we're going to say new state of, so first things first, we're actually going to say we're going to take the back of our states and we're going to say this character C is going to be equal to this new state. And actually we're going to create a new state. So states dot push back a new state. We're going to take, this is kind of tricky. The way we did it before, we said it's actually going to be like this. It's not going to be a new state. It's going to be the states dot size, and then we're going to say states dot push back a new state, which is empty. That's pretty much it. You just create it. So you're always going to have an initial state. And you're going to create a connection for that particular character to to a new state, which is just going to be an integer. Our states are just going to be represented by integers, and then you're going to push back in the back of the vector that a new state, create a new state. That's for all of the sort of regular characters. And then for a question mark character, we can do the same thing, actually. But what's interesting about that is this will match any character, which means you can actually use the same thing. So it's really not, that actually is only going to be in the implementation, I think. Excuse me. Yeah. So we just have to. That's just sort of in the implementation. We can modify what we're going to do with matching any single character. It's not too complicated. What gets interesting though is this is called the glob pattern. What's going to happen here? How are we doing on time? 7 minutes. Okay. The glob pattern is interesting because that we have to have an epsilon jump for when there are no matching characters. This is what's interesting also about this asterisk is it'll match any character. I want to say that you might not even need an epsilon jump. I want to say this is going to loop back this character. Creates a loop back. You can have any characters from there bring you back, or 0. So you're already there at 0, and any character you can come back to the same spot. I don't think you need any other states. Yeah. So yeah. So that's it. So there's actually no epsilon jump here. You don't even need that. And what this is going to say is states dot back of yeah, so you don't go to another state really. The only way you go to another state is that's interesting. So just thinking. Yeah, it's only when you see the next character. It's only when you see the next character. So it's just states.back of C is states.size -1 itself. And that's it. You don't go to a new state. Process state machine with memoization. Which you might not even need memoization. So we're going to say autodfs. It's going to be a function. Oops. It's going to have some parameters. I think we actually can return true or false here, depending on the results are. So we can say a few things, and we can have the states. We can have int current state, and then before that we would have which index or index. So this will be the index into the string, and then the current state, and then we can memoize this as well. So what we're going to do is say base case if, or base cases it would be, we're going to have, well, there's going to be a memoize. We'll come back to that in a moment though. We're not going to memoize first. So if current state is equal to, so if the index is equal to string dot size minus 1, and the current state is equal to states dot size minus 1. So actually the index should be passed. You should have processed all of the string. So if it's equal to the size, so we've got through the whole string, then we return true. And the current state is the last state. That's the ending state. Then we're going to say for, it's going to be the following. So for each, it's going to be const auto p. You can actually do auto. It's going to be the character in the state. So it's going to be the was it key value? So we would say in the current state. So states of the current state. We're going to say if the key is an asterisk, we're going to do one thing. Else if the key is a question mark or something else. We have multiple options. If we're looking at an asterisk, then we're going to return, and not just return, it's really, I gotta think about this. So then we return false if we don't have anything. I'm trying to think how we do this. It could be any of these three. If it's true, we would terminate early. So we would just say if return true. Otherwise, we just keep going. This is kind of the construct we want. We'll get to the memoization shortly. So what we're going to say is f of, we're going to, if we're, so the index is going to increment by 1. Now what's interesting is C. So yeah, so we need C is equal to S of index, and then this here, there's one more else if. Though the first two if statements, let's be charging the headset here so you can hear some noise. The first two if statements can match any character, so we just check if these exist at all. And actually, they're not else statements. That's actually, I think, part of one of the issues here. These aren't else. We say if. We do all of these. No. Well, they're all. It can only be one of these three. So that's fine. That's actually fine. If C is equal to K, then we're going to recurse each of these cases. But it's slightly different each recursion. So all of the recursions are going to have index plus 1, and these are const also, these don't change. I guess this is also technically const. We're not going to change f either. That's probably a good idea to make that const as well. Index plus 1. However, in this case, the current state doesn't change, and obviously f doesn't change. With a question mark, the current state increments. And we could do an or. Either one of these work. So really have two scenarios. Right. So if you have an asterisk, you're not going to update the current state. If you don't have an asterisk, you are going to update the current state. And you have these two different recursions that happen. And we can memoize this over the index and the current state, indices and current states. But I think it's this simple. I think this is it. That's all you got to do. Oh, also return the initial state is going to be 0, and the initial index is 0. Right, start the first character. I think it's that simple. How are we doing on time? 16 minutes in. Okay. All right, let's try this test cases. See if we have any issues, crashing and whatnot. I think we do need to memoize. Runtime error. Okay. Whoa. Stack buffer overflow. Is that what happened? Buffer overflow. There you go. Stack overflow. Oh, yeah, I know what the problem is. Yeah. I did this wrong. There's always something when I'm working with like DFS related code. There's always some error that I make. But this is the issue: is that we must stop if we're greater than or equal to size. That's why it's overflowing. Is it's going infinite. It's going infinite. There you go. Sample test cases. Oh, 1, 2, 3, 4, 5. So the problem with this, though, is while correct, I don't think it's going to work for. I don't think it's going to work for very long sequences of things. Well, actually, what's interesting is you always increment the index forward, no matter what. So I think even in these recursive cases, even though I'm trying to think, why would no? I mean, how? Trying to think here. Well, you can't have more states than you have. Like S doesn't. Yeah. Well. Just thinking. How do we? I don't know what the runtime is. That's the problem. If this is efficient enough, we could just hit the button and move on. But if the runtime, if we need to memoize this, maybe we need to memoize it. The problem with memoizing is I really don't think there are too many. Okay, let's say with a glob pattern in the beginning. And so now we have this recursion here and then this recursion here, right? So you do both, and then you say, okay, I'd really only like, actually, it's only the glob patterns that could even give us some extra recursion, and the glob patterns themselves are like, you can't have multiple glob patterns, so really all you have is just like these states are pretty simple. They're actually just a straight line across. Like it's not a graph. It's just a straight line across left to right. And in some cases you have a glob pattern loop. Which you would recurse on both. I'm trying to think though, how do we like address that, or how do we handle that in a way that's efficient? Well, I guess you just have to have something that has like multiple glob patterns. By the way, once you hit a glob pattern, no. You have no, that's not true. I was gonna say once you hit a glob pattern, you're done, but that's not true. Because you might have like a suffix that it ends with. Just trying to figure out like what the runtime of this is without memoization, and what the runtime would be with memoization. Because you have 2000 and 2000. Like let's say you have 1,000 glob patterns, right? Like 1,000 asterisks, and then you had, so 1,000 characters and interspersed would be 1,000 asterisks. Like that would probably be the worst case. That basically means that every node in your state machine just has a loop back on every node, and also one loop forward, or one character forward, and that would match a lot of different things. What I'm wondering is how efficient or inefficiently can we do this? Well, in the first case, you can process any number of characters and then jump. And each time you potentially process, you basically have another iteration here where you have index increments to the next character, but you're either starting off at you're starting off at another, I guess it would be 0, state 0, and you have another sort of iteration. So yeah, you can kind of increment index +1 to any amount forward from that state. And then all of those iterations would need to happen. Really, that's at most. There's only an index, S O of n iterations there, and then each of those. Now the problem though is that once you get to the next glob pattern, yeah, you'd do the same thing again, but with just a slightly different different current state value. And yeah, you're going to want to memoize that. Does that give you exponential time? I think it does. Because each of those would then do that, which is kind of a lot. I think it's actually more like factorial or something. It's a lot. It's not necessarily exponential, but I don't know what it is. I don't know. Yeah, basically every time you see a character with an asterisk, you have a sort of a split, and so yeah, you could end up with something that's like 2 raised to the 1,000. But the problem was that if we had 2,000 by or 1,000 by 1,000, it would be more like memoizing. That's still relatively inefficient, but I guess it's reasonable. So we'll memoize this. So let's actually just test that now for 2,000 characters. So we'll write a quick script to that test case. It's kind of a special test case. It's going to take us probably more than half an hour, because I still have to debug it. But we weren't going to try to memoize this, but now I'm going to. So we're going to use an awk program. You actually don't really need to do that. Yeah, actually it's fine. Awk, and we want so what we're going to do is have 2 lines. We're going to say just A to Z. So Can we do like, does awk have code points? Kind of curious. Let me see something here. This might take a while. I was hoping this wouldn't take so much time. Okay, we have the arrays, functions, built-in. Oh, okay. Built-in function summary. Okay. Come back to that. Calling built-in numeric functions, string functions. We're looking for like code point related functions. Turn on the numeric functions. String functions it must be. Also how to call built-in functions, that would be useful too. String manipulation, query details. A sort, elements in the array source, sorts the values, gawk, okay, gawk sorts the values, excuse me. That's interesting, these associative arrays. Cul-de-sac. Indices are sorted instead of the values. That's really interesting. We want index, length, match, pat split, split. This is like in Python. Sub string to num. Oh, there we go. That's what I want. 17. No, actually, that's not what we want. That's not a code point. That's not exactly what we're after. Lower to upper split. Oh no, does this not have code points? No. No. Is there no way to do this? No. Can I use an awk script to generate my, I don't want to write a Python script to do this. I like just writing awk right in the shell. Well, you could do something similar where you could just use an array. You can kind of make a custom version of this. That's right, we're not going to get so hung up on the code points. What you can do is just create just array, or not array, but just like our alphabet. So alpha, we'll just say A, B, C, D, E, F, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Actually, you know what? I have a program already to do something like this. Genran numbers, I think I have. Oh no, I want genran characters. Yeah. Also, forgive me for all of the. You probably hear that. Oh no, I don't think you can hear that. I think I have to turn it off. Yeah, you don't hear the desktop audio. We'll do 1,000. Okay, we have random characters, and then we're going to vim. Oh, I see. We could do this. We could just do echo awk. And we're going to just say print x. Print x. Echo awk print x for I equals 0, I is less than 1,000, increment I, do the following in this loop. We're going to have x equals an empty string. We're going to say x equals x with a question mark and an asterisk. So just over and over and over, question mark, asterisk. There you go. Okay. And copy this. So this is going to be our next use case or test case. And the idea is that I'm expecting this to time out. I just want to test that it will. And then we're also going to test a memoized version of it. That's the issue here. That's the main issue. And we go back to our characters. So we have 2,000, actually it should be 2,000, not 1,000. So we have 2,000 characters randomly generated, and we also have okay. Okay. This should time out. That's what we're expecting. Oh. No kidding. Right. That's interesting. Do we even need to memoize this then? Which program was this? Oh, we don't need the stack dump. Gen numbers CPP. Let's try that. I don't know. We're just gonna put like wildcard matching. So this is a little bit weird what we're doing. There's something specific we want. We want to do two things. We're going to say 1,000. We're going to generate. We're going to do two things. We're going to say so we're going to generate this random character twice. So 2 strings. We'll have string first and second. 2 different strings. And the first string, first, second. And we're not going to run this loop here. And it's going to be like something like the following. First plus equals. And then the second yeah, so this is kind of tricky. So we're going to randomly generate a character. We're going to put that in the first string, and we're going to put that in the second string. However, the first string is going to get another randomly generated character, which we're going to paste. And the second string, instead of getting another randomly generated character, is going to get a it's going to get another randomly generated character. Or no, it's going to get an asterisk. Yeah, I'm trying to get a very specific thing going on here. So this is also deleted. I think I have to kind of practice with Vim a little bit more. But we're going to get 2 lines now. One of them is going to be a randomly generated character, and then another randomly generated character, and the second is going to be the same first randomly generated character with an asterisk appended to it, and then we're going to print both of these lines. So that's what our program's going to do. So we're going to compile this. We're going to G++ gen characters wildcard. Hopefully compiles. And then we're going to print with 1,000. There we go. Okay. Now, what's interesting about these 2 test cases, I think this is also going to happen very quickly. I think this also will not be a problem. But what I want to do is basically like manipulate these 2 test cases. Oops. So this should return true, and this should be kind of quick. What I'm looking for is a situation where it's not that quick. I probably should just memoize this and call it a day. Realistically, not thinking about it. 40 minutes now. Yeah, because these are both true. But if we take this test case and we just kind of manipulate a bit. Just randomly change some characters. Just change a few different characters to something else. How about that? See if it goes any slower or faster. If there's any change. I would think this wouldn't be that fast. TLE, there you go. See that? That's what I was looking for. Yeah. 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 Yes. That's what I was expecting. So we can use a, we can memoize. So this is going to be size t, operator this guy, and this is also going to be const no accept, and the thing that we're going to take in is a const standard tuple of 2 ints t, and at this point we have actually seen this a few times. So we'll have size t, and this is also standard size t. H1 is going to be standard hash of an int. We're going to create the object and then run it on t, which is standard get 0 of t to get the first element. Same thing with the second element, and then we just return H1 ORed with H2 bit shift to the left 1, and that ought to do it. So we have custom hash. We're going to have memoize over here. Standard unordered map of standard tuple ints mapped to Boolean. And we're going to also use custom hash to do that. And this is going to be called memo. And we'll say if memo.count of the key make a pair of the index and the current state. The count of the key is non-zero, then return memo of the key, and anywhere we set values, we're going to also set memo as well. And that ought to do it. That should be a lot faster for us now. Oh, it's still TLEs. Oh, whoa. Uh-oh. Uh-oh. Oh no, this is what I was afraid of. This is what I was afraid of. Oh no. Oh no. That's not supposed to happen. Uh-oh. Is it in an infinite loop? It can't be. Uh-oh. Uh-oh. Oh no. Now we can memoize this a little bit better. We don't necessarily need to use an unordered map to memoize, and nor do we need an unordered map for the state machine. Excuse me. We can actually subtract from the characters, and then these different values. They could be basically they could be converted. So, like here, when we check, we say if it's any character, if it's this or this. Well, we can. I guess what I want to say is like we can. Well, actually, it could really just be an array of 2 characters. Each of these states, and yeah, the first character is either a question mark or any other character, and then the second character is an asterisk, and depending on what we see. But storing that doesn't need to be stored in an unordered map. It could actually just be like just 2-character array, and I guess booleans as well. A 2-character array, or two, I don't know. I'm trying to think how we could do this. The int would be the next state that you point to. It always just goes to the next int, so it really doesn't have to even be it's always just the next state, so you don't really need an integer that you go to either. So you can optimize like the states themselves. They could just be integers, and you could have instead of characters, you could just have, yeah, you could have just like an array of 2 characters. So you have a vector of 2-character arrays, and then you basically have I don't know, I guess the default would just be 0 for the characters, right? A null character. And then if you have, you know, just depending on what the 2 characters are, one of them would be, the first character is going to be either a question mark or some other character, and the second character is going to be an asterisk. So I don't know if my algorithm is fast enough. So it's kind of a problem. The next thing is you could say something like so in order, you could process this differently where it is a lot more efficient than what I have. I mean, this is kind of like somewhat of a more general approach, a more brute force approach. This might just be not fast enough. So you could modify the unordered map to just like 2 characters, an arrays of 2 characters, and then you could also say the hashing too. Memoization, the hash. I guess that's fine too. I guess that's okay. Let's think about putting that into a vector as well. So one issue is, yeah, this just gets called too many times, I guess. Another approach, so this might not work the way I don't think I made a mistake here. I think it just doesn't work. Even if I optimize slightly for not to use unordered maps, because they're a little bit slow, and not to memoize on the index in the current state. We could use just a regular map, that works too. Could also do that. But I think it's just too slow as it is. One other idea would be, I mean, we could try with just a regular map. Try that. Another idea is just a totally different approach. You don't need a hash if you do it this way. Might be a little bit faster. Oh, wow. Hey, yeah. Significantly faster, huh? Let's try again. What I'm wondering is, should I use this? I could try this. Could try this. Looks like I'm not going to be able to do any better than. Looks like I'm not going to be able to do any better than an hour or two per problem for hard problem, even for problems that I think I have an idea. Could use not unordered maps. I'm wondering. I don't know. I'm afraid to do this. There is another approach you could take, which would be like, for each asterisk, there's a string that follows, and not including the wildcards. And you could just say like substring the pieces between that are asterisks. So you would say, like, basically find a substring. So you find the first substring up to the asterisk, and then the next string following the asterisk, you would then perform that substring search from that point after you found the first substring. And then you would, if there's a question mark, you would just skip that character and then you'd substring again. So you can sort of have a sequence of skips and substrings that you would process. And that would be very efficient. The problem with that, though, is you may not be able to, like, that'll only take the first substring that you find that works. That'll only find the first substring that you find that works. And it may be the case that there's a substring later that you should have taken, which is kind of what this approach does. So I think actually that second approach I was just thinking of, it might be more efficient, but I don't think it's correct. We're going to try this to see how it goes. We might not get it. Might be my TLE. Oh, we got it. All right. We're 7% of solutions. Nice. Well, we got it. So yeah, that's kind of an ugly one. I'm not sure about this. Let's try to change how we're handling these states. Yeah, let's try that. So we can say these are just two characters, either a loopback or a specific character. So we do character array size 2 is the state. And the int that we go to, we always know what that is. So now we have, for each state, we don't actually need to push back. We'll create a new state. Can we do that? Can we create a state that way? I don't think that makes sense. Can you push back a character array? I don't know if that works. I don't think we can. I don't know. Can you do a vector of arrays? I don't know. What does this do? Let's do this for a moment. Fun with the C++ compiler. Brackets are not allowed here. Declare an array and place the brackets after the name. Oh. Oh, okay. We also can just go ahead and comment this out too. Learning about the C++ compiler. Declare an array, put the brackets after the name. Huh. So I'm curious what happens if we do that. I don't think that works. What are the rules for the type def for C++? Hmm. Excuse me. Typedef aliases. Different syntax, also applicable to type template names. Okay, I probably want to use a type alias. More complicated typedef, int t, int pointer t. Simple typedef, following two objects have the same type, long L1, new long L2. Okay, more complicated typedef, the following two objects have the same type. So this is int array t of A2. Oh, I see. Interesting. Oh, well, that's a little weird. So you can do state 2, character state 2. Array type cannot be value initialized. Can we just say state? What happens there? What happens if we do this? Let's look at the sun in my eyes now. Sun in my eyes now. Unexpected type name state, expected expression. So let's go to our vector. Can we push an array into our vector? Where's pushback? Where is pushback? A reference to a value. So, like if we have just some state, new state, and we push back our new state. Because I don't know how to initialize like a character array. Compilation error. Yeah, I don't think that works. New cannot have an array. New cannot have initialization arguments. Yeah, I don't know. Huh. Can we increment the size of the array? How do we? I'm really confused. How do I push an array, a vector of arrays? How do we do that? cvref vector of arrays. How do we? We could use a container, maybe. I guess use standard arrays. Doesn't decay automatically. Okay. Interesting. Maybe I just need to do that. I know I can do that, but I kind of felt like maybe I could have a vector of like C arrays. The problem with this is I think you actually would do something like this. Yeah, I don't know. I don't actually know. I don't know. I don't know how it's supposed to work. But we can use, we can do this. This is a little bit easier to handle. How about that? Let's try that one. I do it on time over an hour. Okay. Yeah, there we go. So, all right, we can do states.pushback state. I think we could just initialize that. I don't know if we need to initialize that at all. Let's see. Oh, it does work. Okay, sweet. All right, so now what we can do is modify this code to say for each character states.back, we want to say 0. So if we see, yeah, so we're going to update this code to do the following. So an asterisk will be at spot 1, and otherwise will be 0. And this is going to just be set to true, more or less. That's the asterisk. And this character is going to be set to C. And we just push back a new state. Yeah. So whatever it is, if we set to C, and then when we process, we can then do something like the following. And here, it's not case, it's for each character in that array, really, is what it's going to look like. You could have a auto reference S or state, current state, or something like that. I don't know. Say array or current array is equal to this. It's a little bit easier to think about. And then we can say current array. Now really this is going to be from 0 to 1. So for int I equals 0, I is less than 2 plus plus I. And now we say character k is equal to current array of I. And we'll say if k is at the asterisk symbol, right, so there's 0 or 1, then we perform the following. Otherwise, if k is something else, then you have this going on, and I think you have the same logic. Could be wrong. There you go. Okay. Is that faster or slower is the question, though. I think that might be slower. I was hoping that'd be a little bit faster, but I think it's actually slower because you double these two. I think you really don't need a for loop. You could just say, you can go the other way around. You could do, well, yeah, I mean, it's either or for both, right? I mean, you could have one or the other, You don't need to have both of these, so they're not really related to each other. Also, the initial values should be empty, I think, for both of these, by the way. I think by default they're 0, but I don't know if they're always, there's technically uninitialized, so they could be kind of anything. Very unlikely that you'd randomly have the, let's do it this way. Couldn't hurt, right? Couldn't hurt to do this. Guarantee you're not working with uninitialized characters, uninitialized values. It's really uninitialized pointers, I think, that have the issues. Whoa. Whoa, that might just be too slow. That's apparently a lot slower. No, not always. I actually think it's fine. I don't think we need to do that. But this might time out if I try to run this. I don't think this is faster. I think this is slower. Nope. Just a little bit slightly faster. Slightly less memory. Okay. Great. Didn't really save us very much doing all that. Didn't really save us much. We could just go back to it then. Didn't really matter. Okay. All right, so I don't know, man. I don't know, man. Okay, we'll look at the discussion because I don't know. I don't know how to do this faster. I don't know. We got it, but it was kind of ugly. Kind of ugly. Kind of ugly, in my opinion. What do you get for the discussion? Linear runtime and constant space solution. Whoa. Also, it's a woman. A woman. A woman. Constant space. Whoa. No kidding. 13 lines, O of P plus S. C++ DP solution with a trick. I just memoized, man. Wow. Linear runtime and constant space solution. Whoa. This is from Wildcard matching HTML, Blogspot, Ucoding. Oh, okay, she got it from somebody else. It's okay. All right, well, like, it's all everyone ever does anymore. They just copy somebody else and say, oh yeah, I'm so smart. Look at me. Like, yeah, okay, great. But at least she gives credit, so that's good. Wow. One pointer for the string, one pointer for the pattern. Algorithm iterates at most length string plus length pattern times. For each iteration, at least one pointer advances one step. Use elegant solution in C++. Remaining characters in the pattern. I rewrite in Java. Very difficult to understand, especially the use of variable star and match SS. Test case by hand, I was able to get the ideas without posting my notes. Yeah, I'm not going to be able to figure that out from what they described here. I mean, maybe I could figure it out, but actually, well, let's first try. Let's try. So is match. That's pretty wild, though. I was not expecting this to be such an efficient solution. My solution is quadratic with quadratic memory. Nowhere near as efficient. Advancing both pointers and both characters match or question mark found in the pattern. Note that asterisk P will not advance beyond its length. Okay, so both, if it's either of those, both pointers, okay. Found in the pattern, track the index, only advancing the pattern pointer. Okay, so star, I don't know what star is. Star is a pointer. Equals P++. So if we increment star, SS equals S continue. Okay. So there's some while loop. While you have characters in S, also it's kind of interesting. Const character pointers are kind of unusual. Not unusual, but they're like you're only moving forward the That's super interesting. Okay. Current characters didn't match. The last pointer was a star or an asterisk. Current pattern pointer is not an asterisk, only advancing the pattern pointer. If star, continue. Current pattern pointer is not star. Last pattern pointer was not asterisk. Characters do not match. It's also confusing, the asterisks and the stars and all of that. So when you get false, there's no match. Check for remaining characters in the pattern. I mean, this is unnecessary, right? Oh, I see. While this is the case, you can keep incrementing the pattern. Okay. Return not asterisk p. So, so when you take the character at p, if p is pointing to some character, so we got all the way through the pattern. Right, so p really should be like the null character at the end of the string, right? You take not, and that means true. We got all the way through the pattern. So this is while we have something in S. So we got all the way through S, and then obviously if we have asterisks. Oh, I see. If you have asterisks, you can just push p all the way to the end, and then return not p. Okay. But the question is, how do we prove that this is correct, right? This is pretty simple, this part, but the asterisks. So it's true that we always increment the like at every iteration, we're gonna consider the next character, right? So we're always gonna increment s. But what's weird is there's an SS and there's also a star. These two other pointers. So what do they do? That's like, this part makes sense, but these two parts of the word, this is like where the magic is happening. These things I kind of understand, but these two I don't know offhand. Excuse me. So if you happen across an asterisk, you have some star pointer that's going to move past, excuse me, you're gonna move the p pointer forward and past the star, and you're gonna set star to where you were. That's like the previous star asterisk pointer. We'll call it star. That's previous star. We'll call it star. Previous star. And you're gonna set SS to S. So SS equals S gives you. I don't think these are correct, by the way. I think there's actually these test cases that you could conceive of that would cause problems. I think, I could be wrong, but I think you can in theory. But SS equals S, that gives you set a pointer to where S is currently pointing to without advancing S. So you advance the pattern pointer, but you don't advance S. And you set a star pointer as well. And then you can keep going. Okay. So you don't see, so the current characters didn't match, and you don't see a star. Now, that's if there is a star. So let's say if the pointers didn't match and there was no star involved, then you would just fall through. I don't know, asterisk involved. But if there was some asterisk set somewhere and the characters didn't match, so last pattern pointer was a star. Now I guess my question is there any point where it's like, what happens after you find the star pattern? Like if they keep matching, excuse me, then you basically just ignore the star, right? If they just keep matching until the end. But let's say there is a star, and let's say you didn't match now after you saw the star. So you have a star. P is going to be star plus 1, and S is going to be plus plus s. So your increment s, and you basically backtrack s to plus plus s. I don't think that this is O of the length of the string plus O of the length pattern times. Or maybe I guess maybe I'm wrong. Yeah, if at each iteration at least one of the pointers advance, then I guess that's true. Okay, I guess that's fair. This is a super interesting approach. Current pointer, pattern pointer is not star, only advancing the pattern pointer. What's interesting here is this actually is not true what she said, I think. You have to really like think about this. I don't think this is correct. In terms of like how fast it is. I mean, it's definitely a lot faster than what I did, but it's not as fast. It's not. I don't think it has the asymptotic time complexity that they're suggesting. I could be wrong, but the reason is that you're moving p back to star plus 1, and you're moving s back to where s was set before ss. So like you could move you could move O of n over 2 characters forward, and then hit this case, and then have to jump back. And you could do that actually roughly O of n times, O of n over 2 times, I think. And well, I guess the only reason why you wouldn't be O of n, even though you could end up doing that, where it jumps back O of n over 2 characters, the problem is that all those characters in between necessarily could not have had asterisks in there, which means that, so if this is a correct algorithm, which is that too to consider, if it's correct, that means that all of those n over 2 characters are not asterisks, so this couldn't have happened that many times in between. So that's interesting. Yeah, the asymptotic time complexity analysis for this is pretty nifty, pretty interesting, but this is actually a case where she's wrong, her statement here. I guess you could say at least one of the 4 pointers. I guess that could be true. So all 4 pointers, one of them, that would make you O of n. I don't think this is correct though. I think it's still O of n plus n plus O of s plus p, or we'll say length of s plus length of p. But I don't think it's exactly. I don't think this is exactly accurate, because all of these pointers need to be, so in every step at least one pointer moves forward. So here 2 of them move forward, here the star or p moves forward, and here p takes star state, so it actually could potentially move backwards, probably moves backwards, and then s actually moves backwards, but ss gets incremented. So here ss gets incremented, here star takes the value of p, and p gets incremented. So here ss gets incremented, here p gets incremented, here s and p get incremented. And star, and then star itself actually never get. There are cases where star doesn't get incremented. It just sets itself to whatever one of the other values are, but you can't really go backwards too much, because it'll eventually get updated to one of these other things that are incrementing, right? Increment by 2, increment by 1. This gets incremented, yeah, in every step one of the 4 pointers gets incremented. So even though star updates itself to p and star, as long as you're updating yourself to at least one of the other pointers, and all the other pointers are incrementing, then you can show that you're incrementing at least 1 pointer at every step. That's the at least amortized every step. I think that's the correct analysis to show that this is linear. But I think saying what she said here is incorrect and misleading. Probably why this guy had to like really think through it. But yeah, so what ends up happening is you end up jumping back to the previous index. Right, so you end up jumping back to your previous index. So yeah, so if your characters are no longer matching though, then you would jump back to your previous index to see if there's a star that can be used, right? So we're going to absorb these characters with the star. The way we're going to do that is we're going to update our pattern past the star and update our string to, although keep the star position, update our pattern as one past the star. And what can happen is if there's multiple mismatches, then it'll just keep updating to, the pattern will stay in the same spot. But we're going to keep updating keep jumping back to that star position, and we're going to update S to SS, incrementing. So actually what's interesting about this is I really think this is very similar to what I was describing before about taking each substring. I think this might be the same algorithm. I don't think this is correct, by the way. I think there's a way to break this. Because if you run into like, basically you have stacks of multiple stars, star patterns, something like that. Like that's the issue, is that there could be like multiple scenarios where this doesn't work, something like that. I think one issue is because the stars can match every character and any number of them, you can get a little bit more like wily with what you do. So I take it back. So maybe I'm wrong. Maybe you do only need to go one deep. Basically say everything that doesn't match, you just collect it up into one star and then move on to the next sequence of characters. But I guess what I want to say is like, you could trip this algorithm up by, and I think so, I think you can, by collecting some portion in the star, then there's some portion that matches, and then there's some portion that should have been collected by the star. So the star should have extended. So in other words, the greedy version of this fails, but it shouldn't. Or not the greedy, or the non-greedy version of this fails, where the greedy one should be used. Something like that. In other words, if you have something like this, I think it can actually cause this to fail. And it would do the following to cause failure. So you would say, you do something like this. So you do like ABC star, ABC, and then XYZ. And what would happen is so the pattern is the second thing. Okay. So let's say we did something like the following, where what I want to say is that we match for a time, and then we have this asterisk. So we have, we'll say like T, 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 and then A, B, C, X, Y, Z, and then T, T, T again. T, T, T doesn't work. This does match, but then this no longer matches, right? And you'd actually get a failure, I think, or false. Well, maybe what happens here is that actually it would fall back on the previous star again. So it would actually just include more. But the thing is, like, I'm pretty sure you would. Okay, I think I understand. I think I understand what's happening. So basically what this is doing is it's absorbing some characters, like processing some characters, then absorbing as many failing characters as needed for the asterisk symbol until you see symbols that start to match, and then you process those symbols normally. And then if you fail again, you would actually go all the way back to your you would actually assume the previous characters that matched would be consumed by the star, and then the new characters you're matching that don't match would also be consumed by that same star. I think that's what's happening here. So instead of, you actually kind of switch from assuming that you correctly match those characters, you're now actually going to assume those are matched by the star, and you're going to jump back again to where you were before all of those matches were made. That's what the SS is. And then now these new unmatching characters also get consumed by the star, so everything gets consumed by the star until you get something that matches again, right? So you keep trying until you get matches, and then something doesn't match, and just everything gets dumped back into the star that you were at previously. Until two things happen. Either one, you get through the string and you're done, or you see another star, and you would say, yeah, or you get through the string, right? Everything matches, or you match correctly and then you get another star. So you have two options. Either don't match and that all gets consumed by the star, and then if you finish the string and they're all no matches and you still have stuff left in the pattern, then it's false, right? You didn't match. So everything was consumed by that star, but you needed some other stuff to match to in the pattern. Or you do get some matches and you advance the pattern a bit, and you either advance all the way to the end of, so one issue could be, what if you get through the pattern? Well, if you get through the pattern, and there's still characters in the string, that's a tricky thing, because that could happen. So at some point, note that the pattern will not advance beyond its length. Yeah, that's an interesting point. So if there's a star, then that pattern will end up back at the star. So that's actually considered a failure, and it would actually jump back. It would say everything. So if you get to the end of the pattern, matched everything, but there's still stuff in the string, then actually the star pattern will consume the rest of the string, more or less. Basically, the pattern will come back, and we're going to start consuming the stuff through the star. Yeah, so S will jump back. Basically everything you got up to that point will be consumed by the star from the larger string, and you're going to jump back and have to try to match again. Which is interesting. Yeah, these are all unique characters, so I guess what I'm wondering, maybe if you had like ABC, ABC, and you consumed all of it, but you only had another 3 ABC. So I think you can trip this up. I think you can devise a test case that has issues here. So specifically, if the end of the string needed to be ABC, ABC, right? Excuse me, ABC, ABC, and over here you had ABC, 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 and this is coming after a star. What I think would happen is if you had ABC, ABC matches here, and we're just going to say like XYZ over here. So XYZ star, right? This ABC matches. What's going to happen is you're going to jump back on this star. This whole section gets consumed by the star because it matched here, but we went past the pattern, and you would fall through both of these. Right? Both of these would fail these conditions because P is at the end. and these would fail too because P is also at the end. P wouldn't match any of this stuff. So you would jump to the star, this part in the pattern, and your S would jump to plus plus S, which is here, and then you'd match these three, and it would fail. Right? The pattern, yeah, the pattern would be check for remaining characters in the pattern. Yeah, this actually should fail in this test case. This actually should match. This star should match ABC, and these ABC should match. But I think this code fails. I'll show you that shortly. Let me show you that. Incorrect two. I could be wrong, but I don't think so. Oops. Hold on. Let's do this. Don't think it's correct. I don't think it's correct. Okay, let's do this. Let's do our code, what it would look like. See if we get it right. Okay. So we got true, expected true for this case. All right. Let's see if their code works. I don't think it does, man. I don't think so. Also, we don't need a custom hash anymore. I just want to get rid of all the multi-line comments. That way I can easily comment and uncomment. Okay, now try this out. Also, I don't know if this works for strings anymore. Okay. You could just say S equals, we'll just say S1, S2. I actually don't think this is correct. And we'll see. S and P, oops. So can you do S1 and S2 maybe? I don't actually know. I don't know if it's going to work properly the way that I would like it to. That's kind of annoying. Okay. These are more like iterators over the strings now. You could do something like this. Auto S equals S1 dot begin. Something like this. This will be S1 dot begin as well. Well, S increment, so I think these are fine. I guess you could also say once it gets to the end, I think you just return false here. You could just say so P is not equal to yeah, we could do, you know what we could do actually? I'm doing this wrong. I'm doing this wrong. Let's just do standard string S1, S2. String S1, S2. Okay, let's try that. And then what we can say is, can we get the underlying string? And just go from there. And do it that way. C string. Yeah, this is what we want. There we go. So we can just write S and P as C string. And in that case, I think we can also do this. Let's see what happens if we do this. Oh no, it worked. I stand corrected. I'm wrong. Maybe it does work and I'm just wrong. Maybe I'm just wrong. All right. Well, I mean, if there's a blog post about it, it's probably correct. Usually folks are pretty good about it. Wow, that's a lot more efficient than mine. What I wrote. All right. I guess I don't understand it then. I don't mean to. Let's ponder this for some time. So why does this work? I would expect this to fail in this particular test case. So it doesn't work the way that I was describing. I thought it did. I mean, I thought it would consume this part in the star when it fails. What actually happens if we walk through this test case? So we would XYZ, we get to the star. Then now we're looking at the pattern. Star and A don't match clearly. So we say the pattern is the star equal P plus plus, so star goes here, and S goes to here, right? Our SS is here. Next we say P and S. These match all the way through on P, so we get all the way through, right? So all those matches. So now S is here, P is off the side. P is now doesn't match here, doesn't match there. We get the star, which is still set to this one, A. We set P to star plus 1. Oh, I see. So P. So no, P. Excuse me. Star is actually still here. Excuse me. Star is still here. Set P to star plus 1, and S is plus plus S. SS. Or yeah, S is equal to plus plus SS, which SS we set here to A. So what's interesting is at ABC, SS was set to S, which was this match. So we increment SS to B, I think. Is that right? So increment SS n to B. We said this is where the star was. We started B. That's really weird. Why wouldn't we be at S is at A, SS at the A, increment SS to B, set S to B. So I guess we match A with the star. So we oh, I see. So we tried matching ABC, ABC with the star. Now we're going to try to, so yeah, okay, I get it. So we don't include anything in the star the first time, and it works. Now we include one character in the star. So we say B, C, ABC. And that doesn't match. So we go back to the star again, and we say, there's a star. We set P equal to A. And we increment SS again and set S to, oh, I see. So it doesn't work on ABC, ABC. Then we try BC, ABC, doesn't work. We see ABC, doesn't work. ABC, ABC works, and then you're done. Oh, I see, I see. So actually, you just skip a character at a time from the star until it works, or until you find another star. Oh, that's very interesting. So, but this is actually not, is it linear? That's kind of interesting. So, so it's not what I was saying. It's not actually consume. It's actually you go all the way through, and then if it fails, you jump back and try again. You go all the way through, fails, jumps back. But I think you can get this to not be linear then. If you just do ABC, ABC, ABC repeatedly, do this over and over, right? Just like so. If you did this, basically it would work and then it would fail once you get to the end, right? And then you do 1, 2, 3, it works again, and then it fails again, and then you go have to go 1, 2, 3, 4, 5, 6, because you keep incrementing the SS term. But the thing about this is what I was saying before is that SS will keep incrementing over and over as you keep failing. But the problem I think I was considering was like, well, what if you need to jump back? So I guess you never need to jump further back from the previous star. I think that's true. I think that's always true. That's a tricky thing. That's like, are you sure? Is there ever a situation where you would need to go, you would never go back to the previous star because the star consumes everything potentially. So you can put as much as you want in the star. So really what this is doing is it puts one character at a time into that star and tests and keeps going. But the problem is, what if you don't have the right number of things consumed? Like if you have multiple stars and you don't have the right number of things that are consumed by that particular star. In other words, you get to the next star, but you needed to consume more characters in the previous star. Is that even possible? I'm thinking the only way that you can have problems is that because you're only considering one star at a time, somehow you get the wrong number of characters that you need for that particular star for this to get the right answer. Yeah, that's the issue. I want to say you could break this. I think you could break this. Either you can make it a lot slower than you think. No, it can't be slower because of what we said before about the pointers. You're always incrementing at least one of these 4 pointers. Her analysis was wrong, certainly, but the So the issue is that if you continue matching, get all the way through, you either have two options. Either you have some failing point and you need to consume some amount of characters in the star, and you're gonna brute force each one. And you could go through the whole. I mean, this is also not. I was actually thinking of. Well, no. No, I think I was wrong too about that. That logic that I had was wrong also. You could do this. I want to say, no. Yeah. Okay. I'm sorry. I'm just thinking, because you can go through the whole pattern almost practically O of the pattern over 2, right? You could perform that, and each time you do that, you only increment one character towards the star. So you can end up with O of n over 2 times O of p over 2, which is O of n times p. So this is not more optimal than, it's definitely faster than what I coded, but this is, in the worst case, this is actually also the same running time that I had. Yes, it does use constant memory though, which is pretty good, but I think it's still the same running time in the worst case, because it could cost you the whole, you can go through the whole, potentially go through the whole pattern, p over to half the pattern, p over 2, or some fraction of the pattern, p over 4 or something, whatever it is, some roughly some fraction, constant fraction of the pattern, and then that's required to go through some other constant fraction of the original string, like half the string or half the pattern. And because what would happen is it would fail. It could actually be something that succeeds half the time, not every time, but half the time, succeeds half the time, so that you need to consume in your star like 1 or 2 characters. So yeah, let's see, every 2 characters you use p over 2, which will give you p over 4 operations, right? And that means you have to do that p over 4. You have to do that half of, I guess we did n over 2, so n over 4 times. So p over 4 times you're going to perform n over 4 operations. Or n over 4 times you're going to perform p over 4 operations for all those failures to figure out how many characters you need to consume in the star. Yes, I was actually wrong in my first analysis as well. And the problem is that you're resetting p backwards each time. So no, this is not O of n plus p, or O of size of s plus the size of p. This is actually O of size of s plus times size of p. Size of p times size of s. Now, one upshot though is that you don't use any memory to do this. So this is that's interesting. It's sort of like, because you don't need to. You could say something like you never need to go more than one step. So the problem that I have, or the problem that I had, is that I wasn't sure how deep in the stack you would need to go. The assertion here, so another question is whether or not this is correct. The reason why I think it's correct is because in theory, you never need to go deeper than one stack into the star characters that you're using, which means you don't need to use a depth first search, which means you don't need to use that much memory. This is basically like a depth first search with only one level above that you ever go back to, something like that. Yeah, you can stop immediately. You can basically, some of these branches on the tree are pretty much dead branches immediately under certain conditions, I guess, something like that. So why is that though? So obviously I memoize every single step, but I guess you don't necessarily need to do that. It'll be too slow if you don't memoize, but you don't need to memoize more than like a few pieces of information. Like you only need to keep track of like some previous values, something like that. There's got to be an analog between this algorithm and the depth first search that I wrote, where like I guess you would say this is like this almost would be like the breadth first search, or something like that, or maybe like a bottom up, and then you don't actually need that much memory. You only need a few pointers to do it. Something like that. Something like that. I'm not really sure exactly what the analog is, how to understand it, but I'm sure basically this is realizing that since you don't need to go that deep in the stack, and I guess you could prove that. Then you don't need nearly as much information. You don't need to keep track of all this stuff. But I guess another way of saying is like the only stuff you have to keep in memory would be one. It's interesting though because it's not like traditional kind of breadth first search or depth first search or bottom up kind of approach, because I guess you would always go to the, I don't know, you just always need to go back to you only need to go back to the previous star. That's like the main thing. You don't need to keep any information about any of the characters before or the previous star or any of the other. Yeah, that's actually it. You don't need to keep track of any of the memory before the previous star. Just need to keep track of information about the previous star. Somehow that ends up making this, simplifies this quite a bit in terms of memory. But this actually doesn't. It's more efficient in terms of like how quickly things happen, and obviously it's a lot less code and all that. It's a lot more terse. But it does not. It's not more efficient in asymptotically, which is interesting. But yeah. So why is it? Can we prove that this is correct though? Let's try that. So, I mean, is that true that you don't need more information than the previous star? So there's some amount of characters that you consume. Excuse me, until you get to the either until you finish the string. Don't match the string at all, so it doesn't matter how many characters you consume, it doesn't match at all. Or you get to another star. So let's say in the pattern, so let's say somehow you get to the next star in the pattern. You don't even care about how much you consumed out of your string. So I think that's kind of a problem. I want to say that that's not correct. I want to say if you add more stars into your pattern, then you can trip this up. Let's see if that's possible. So let me think about it for some time. If you have more stars in your pattern, and let's say you consumed only as many characters as you needed in the star in order to get to the next star in the pattern. Okay. Let's suppose that's the case. Is there a way, so you could consume more characters in the star and continue that way. And let's say if you can, so we need a case where you could reach the next star by consuming more characters in the first star, or you can reach the next star by consuming less. So there's two ways to reach the next star. One consumes more characters, one consumes less. Let's see if we can figure out a way, one, that's the case, if that's even possible, and two, that if you consume more characters once you get to the second star, then you can show that it's true, that it's a match. But if you consume too few characters when you get to the next star, then it won't be a match. Now, that might be logically impossible. If we could prove that it's logically impossible for that case to occur, then that means that they're correct. If it is logically possible for that to happen, then they're not correct. Then we can actually use that as a test, as a counterexample. So the problem with that, though, I think it's not logically possible because, like, suppose that scenario, if you could get to the second star, it's actually clear that that you can consume as many characters as you need. So if you use fewer characters and you did get to the second star, any amount of characters that you would need to consume in order to match the suffix at the end, you can just add those to the second star. So actually, whatever if you had too many characters or not enough characters in the first star, then all those characters can just be consumed by the second star. so it's not possible. The second situation would be, yeah, you would just move some characters to the other star, some characters to the second star. Because the stars match any character, they're kind of special. So you never actually need to consider more than the first star, more than the previous star. So that's it. Yeah, you can prove that's true. Okay, so I believe this works. I believe it's true. It's pretty interesting. I would have never figured this out. This is like so beyond what I was thinking. It is special for. It is really special just for these particular characters. You know, the asterisk and the question mark. It really doesn't work otherwise to do this. Yeah, it's because the asterisk is just so, like, it just consumes so much in one shot. The thing on the other hand though is the runtime is incorrect. This does actually have the potential to become O of size of S times size of S times size of P. Because you could say, like, you could just do AB, AB, AB repeated a bunch of times. And you could say that the pattern could be, you know, like half of the pattern is just AB, AB repeated, right? That'd be P over 2. And then S is very large, I guess, and it's just multiple copies of AB, AB just over and over and over again. And you could say that, like, you know, most of it is just that after the star, or no, actually there's no star, it's just AB over and over again. And what would have to happen is you would, every other character in S, so from obviously the B's won't matter, but each A, you're going to have to process that pattern AB, AB, which is half of P over 2. Process that, so it's half the time, which is going to be, we said we could make this like roughly n. I mean, we could do like n minus 1 or something, or n minus 2. It could be like, it could be starting from the beginning, really. And where actually P could be almost all of P as well. But we could just say like P over 2, roughly P over 2, roughly n over 2, or roughly S over 2 in terms of size, size of S, size of P. And you could say, basically, to move from the star to the next character, half the time you have to process P over 2. So it's P over 2, S over 2 times a half, which gives you like P size of S times size of P over 8. Yeah, I think that's true. Half the time you have to process P over 2. And yes, yeah, that's a worst case. That's not O of the size of P plus the O of the size of S. So I was wrong in my analysis before too, and so was she. That being said, it's really efficient in most other cases, and the vast majority of cases very efficient, and it's also does have constant memory, and it is correct because what we were saying before is that all you need is enough characters to get to the next star, and then whatever you might need to add to that next star, you can just add it. So what's interesting is whether or not it's possible to skip checking the sequence. In other words, can you just use a substring sequence? Like, yeah, just take a substring. That gets you to the next star in the pattern. That I think would be a lot more efficient. So yeah, you could do a substring search. And what I would do is, if it's the end of the string, I would take a substring search. Like if it's the suffix we're looking for, I take a substring search that matches that. Now, what's tricky though about the substring search is that you do have the question mark character in there, which makes it a lot harder. So I don't know, because you could have a substring search match not up to the next. Yeah, like you can't really substring search that. That's kind of challenging. I'm thinking, what can you do? Let me think here. If you really wanted to, you could write a modified KMP algorithm that uses a substring search. Modified KMP algorithm that uses the substring search that has a modified character for the question mark, and perform the search that way. And then you can search for the rest of the suffix that you need in the string, and then obviously all the characters previous will be consumed by the asterisk, the star, as needed, and you just terminate there, right? That would be linear. And you could also, that's for the ending. If you just need to get to the next star, you can do a similar thing where it's just the first substring that matches, and then you can get the next star. And that's fine. And so you can repeat the same thing. So if it's between stars, you can do a KMP, modified KMP algorithm for the substring search to get to the next star in the pattern. If it's the last star in the pattern, then you just perform a KMP search for just anywhere. Actually, you should go all the way to the end, and then all the characters in between would just be consumed by the star. And that would actually give you the optimal running asymptotic running time in all cases. This technically won't. This actually, maybe you might only need to do that at the ending. I'm thinking about it, like just for the suffix, you only need to do that sort of quote-unquote KMP search, modified KMP search. I'm not actually sure if you can do that, by the way. I think you can, like use the KMP table, build a table where you can use this question mark character, special character. One issue I think you'll run into is one, whether or not you can actually do that with the KMP algorithm. I think you can, but I don't know if you can. That's one issue. Another issue you can run into is how much do you need to get to the next star pattern? I think you can just do a regular. I think you would just do a regular search. If you, at any point, find the characters that you're looking for, then you can just anything to the right of that gets absorbed in the star character, and then anything to the left also gets consumed. So you can just do KMP searches, substring searches. Pretty interesting. Until the end, where the end has to actually be a KMP substring search all the way on the right side, suffix. That actually doesn't need to be a KMP search, by the way. That could just be do the last characters in the string match from right to left. So actually the substring search really only has to happen in between. And you can do, yeah, the tricky thing with that substring search is that you do kind of want to use like a KMP algorithm search and probably modified because you do want to find like, yeah, you don't want to just like perform a substring search on every, which is actually kind of what this is doing, by the way. This is actually doing like a substring search on every, with just moving the character pointer ahead one, which is not as efficient as it could be, actually. So that's interesting. That's interesting. Yeah. You can do this in O of length of S plus O of length of P time. However, I would say you would use specialized substring searches to do that. Probably wouldn't be able to do that the way that they did this is actually not optimal, believe it or not. It's pretty fast, but it's not optimal. We can just submit just to see what the time is. So yeah, we spent a couple hours on this, but pretty interesting question. But yeah, definitely not yet. Oh wow, whoa, whoa. I think all of the test cases, I guess they that's such a difference. All the test cases are probably not the worst case for this. But even in the worst case, I think this is just using such little overhead that it's extremely efficient. Really interesting. I don't think it's linear, by the way. I don't think so. I don't think so. Not in the worst case anyway. I guess it's linear in most cases, but not linear in the worst case. So pretty nifty, pretty neat. Yeah, this is a lot like performing like a modified substring search from the pattern, like this right from the starting point of the star, and then if it fails, you just consume another. You start from the next spot and just kind of over and over. Really interesting. Really interesting. Yeah, it would have taken me forever to figure that out. I forget it. I would have like never gotten there. Really good problem, interesting problem. I guess we're kind of stuck with like, yeah, we're gonna be spending like hours on every problem because there's just so much to it. All right, thank you for watching. I will talk to you soon. I think I did want to do another problem, I think, before I moved on. Let me. Grateful that somebody dug up this solution. But again, I think there's actually a slightly better solution, even asymptotically, for like the worst case situations, believe it or not. But yeah, let me go. Thank you for watching. I will talk to you soon. Oh, I guess the prefix and the suffix, the prefix you also have to be careful because I think the prefix has to match exactly also until you get the first wildcard pattern. Or not first wildcard, but the first asterisk. But I forgot about that part too, because in all the sequences in between two stars, you can set how many characters get consumed by each star. There's the the pattern in between the two stars. You can kind of just take some substring, the first substring that matches. You just take as many characters as you need and put them in both stars, but to the left of the first star, you don't have a choice, actually. That has to match exactly. But that's actually pretty easy, right? It's just like you just can walk through until you find the first star. And then after that, you could just do substring searches between stars, and then quote-unquote modified substring searches between stars, and then which would be linear. And then finally, at the end, you just do a suffix check once you find the last star. And I guess you could walk through the pattern once, do a pre-processing step just to figure out how many stars there are, just so you know you're at the last star. And then when you're at the last star, you could just do two suffix checks, which also is pretty simple. You could just do that linear, naively do the suffix checks. So the prefix checks, suffix checks, and they could be any characters on the last star to the end, any number of characters as long as that suffix matches. So yeah, I would do it that way. That's probably how I would do it to get the optimal in all cases. But this is pretty good in most cases. Apparently we get 0 milliseconds for the test cases, which is pretty wild. I don't get that too often. But yeah, interesting problem, interesting solution. So yeah, thank you for watching. Talk to you soon. I think we'll pick up another problem. Oh yeah, the next one's pretty easy too. The next one I've seen before is the n queens problem. I'm pretty sure I can come up with the DFS for that. I kind of thought about that already, so that shouldn't be too bad. We'll give that a shot. I might pick up a third problem. Like, we'll definitely do that one. I might pick up a third one. So yeah, thanks again for watching. Talk to you soon. Have a good rest of your day, and take care.